We're here in Cambridge in the UK to meet with George Efstathiou. He's a co-winner of the Shaw Prize in Astronomy. He's receiving the award for his pioneering research on the fluctuations of the cosmic microwave background, the oldest light in the universe. On this summer day in Cambridge, astronomer George Efstathiou takes his 1970s vintage car for a spin in the neighborhood.
It's a small little MG sports car, classic British sports car, and it's a lot of fun. So that's one of the things that I really like to do.
And he also really likes to study old things from when the universe was formed. His interest in astronomy began at a young age.
As a young child, like many children, I would ask questions of, what are we, why are we here? And then you look at the night sky and you ask questions about, the universe, where does it end, and so on.
When he was 10 years old, he discovered a picture of the Hale telescope in a children's encyclopedia. It was the largest telescope of its time.
I was amazed that people were building this enormous telescope with a mirror that was 5 meters in diameter to study the universe. And that was, for a little kid, that was inspirational. And so I have a copy of a Porter print in the office here at work, and a similar one in my study at home. And that's a permanent reminder to me of why I'm doing astronomy and cosmology.
A child of Greek Cypriot immigrants, George received a bachelor's degree in physics from the University of Oxford and a PhD in astronomy from Durham University in the UK. Then he was a postdoctoral fellow at the University of California, Berkeley in the US in 1979. That's where he met John Richard Bond, or Dick, the Shaw Prize co-winner.
I regard Dick more like a sort of brother than a fellow scientist, because our relationship was so close.
They set out to unravel the mysteries of the cosmic microwave background, the oldest light in the universe.
This shows Arno Penzias and Robert Wilson in front of their receiver, and they detected, in 1965, they detected excess noise in their receiver, indicating radiation that was coming from, that was the same in all directions of the sky, suggesting that it was cosmological in origin. And what they had discovered was the cosmic microwave background radiation.
The cosmic microwave background radiation, or CMB, is light left over from the Big Bang that gave birth to the universe. The light comes from when the universe was 380,000 years old. Immediately
After the discovery of the cosmic microwave background, various theorists, including Jim Peebles and Zeldovich, realized that there had to be little temperature differences in the cosmic microwave background. When you look at the universe today, you see galaxies, you see groups of galaxies, and so on.
Fluctuations in the CMB evolved to galaxies, stars, and planets. Many astronomers try to solve these physics equations about the evolution of the CMB.
So we were the first to actually solve these equations, with inflationary initial conditions, doing the general relativity for the way that gravity affects the photons. And amazingly, the universe with inflationary initial conditions, cold dark matter, and dark energy, turns out to describe our universe very accurately, not just in temperature, but in polarization as well.
The inflation theory believes that the universe underwent a period of rapid expansion, from submicroscopic to astronomical size in the first few moments after the birth of the universe. But colleagues were skeptical about George and Dick's calculations on the cosmic microwave background.
A lot of people didn't take inflation very seriously. They didn't take dark matter, cold dark matter, very seriously. And the fluctuations in the cosmic microwave background hadn't been detected. And so You know, the sort of things that we were doing were looking at, long shots theoretically and predicting effects that were very small and hadn't been observed.
Data didn't exist yet to support their theoretical predictions. The evidence would be discovered years later. George and Dick's careers took them in different directions. Dick remained in North America, and George went back to the United Kingdom, but they stayed in touch. George returned to the University of Cambridge in 1997, and later founded the Kavli Institute for Cosmology. George and Dick reunited to work on the European Space Agency's Planck space mission from the late 90s to the launch in 2009.
9, 8, 7, 6, 5, 4, 3, 2, 1, top. Allumage Vulcain.
And it was just a spectacular thing to see. When the big rocket goes off, you feel it inside you, you know, as vibrations and so on.
The mission was to observe the cosmic microwave background.
This is the sky as we detected it with observations from Planck.
So this is the universe.
So this is the universe. So it's an image of the sphere around us. So it's a snapshot of the universe as it was when the universe was 380,000 years old. So very, very early on in the universe's history.
And what are the blues and the reds?
Yes, okay, so the red dots are where the temperature of the microwave background is slightly hotter than the average, and the blue is where it's slightly colder. And the fluctuations themselves are very small. The variations are of about 1,000%.
But what is the significance of this? So did these temperature differences evolve into planets and galaxies?
Absolutely, absolutely. This is these are the small fluctuations that grew to make everything that we see in the universe today. Planets, stars, galaxies, everything.
The data was remarkably similar to George and Dick's calculations in red.
The red here are theoretical predictions based on inflation, cold dark matter, and dark energy. And the blue dots here are the measurements from the Planck satellite. And you can see that the blue dots here are in perfect agreement with the theory, which is really remarkable. And it's actually quite rare in physics that we get theory and experiment in such good agreement. Calculations that we did are exactly what the universe is like, and have been verified to high precision, including the polarization of the cosmic microwave background. So you know, I think we were lucky.
His graduate students said George was more than just lucky. He has great intuition.
And that sort of intuitive understanding, just really understanding the physics better than anyone else working on the problem at the time, along with Dick Bond, I think was the real advantage that gave them the sort of skills to be able to go on and produce this work.
ED at 2.6 sigma.
Stephen Grattan is an astronomy professor at the University of Cambridge. He says George's work on the cosmic microwave background helps to answer the big questions in life.
George's work and George's contribution to this endeavour has been really important and really helped the field understand the universe. Being like, how old is the universe? What's going to happen in the far future?
The answers fit what is now known as a standard cosmological model of the universe, or the Lambda CDM model. Age, 13.8 billion years. Geometry, flat. Composition, 5% ordinary matter. 27% cold dark matter. 68% dark energy. But there's still a lot more work to be done. Scientists are scrambling to figure out what cold dark matter and dark energy are. Back home, George likes to host friends and family for barbecues in his backyard. Years earlier, George met his wife Yvonne, a librarian, at a formal dinner in Oxford.
And so I thought he was quite interesting. I thought he was quite handsome. And we started chatting, and that was it.
It's a bit sad, actually.
They moved to Cambridge and bought this house almost 3 decades ago.
Happy kids.
And they have 2 sons.
So it was a lot of my mum doing the stuff of like taking us to school, taking care of us, whereas my dad, for as much as he can like work on a satellite, would struggle to use like a washing machine or anything.
But now, the kids are grown up, and I do the lion's share of looking after the dog. So it's true. It's true. So there's, you know, things evolve.
George is retired from the University of Cambridge now, and he's excited about the new chapter of his life.
And when you've got the freedom to do whatever you want to do, the thing that really I love to do is to solve problems. So, and that's not going to change. So I'm going to be solving problems until I die.
When we return, we'll meet the co-recipient of the Shaw Prize in Astronomy in Canada. Stay with us. The co-winner of the Shaw Prize in Astronomy is a Canadian researcher. His theoretical calculations of the cosmic microwave background from the 1980s were verified by data decades later. We're here in Toronto to meet with John Richard Bond. John Richard Bond, astronomy professor, University of Toronto, Canada. Dick is passionate about cosmology, the study of the universe.
The most astounding thing is that we can actually understand the universe at large, given what we are as these tiny little things on this surface of this planet, right? It's actually hard to believe.
A graduate of the University of Toronto, Dick has worked at the Canadian Institute for Theoretical Astrophysics for 40 years. This optical telescope is a pride of the department.
What it's used for is to help undergraduates to understand that astronomy is just not what you do in the classroom, but it is what you can see on the sky. And so this plays a role in the mentoring of undergraduate students.
So what can you see with this telescope?
Well, you can see planets, of course, and you can see, you know, stars out to some distance.
While Dick's colleagues spend more time observing the universe, he is what's called a theorist.
A theoretical physicist works with equations and the mathematization of reality in order to try and understand what's going on from the information that the universe provides for us.
Friendship underpins a lot of his work. George Efstathiou, the Shaw Prize co-winner, is one of Dick's closest collaborators.
Friendship, in my view, is scientifically, it's the most important thing.
During their postdoctoral fellow days at the University of California, Berkeley, they started working on a great mystery of the time, the cosmic microwave background. The CMB is light left over from the Big Bang that gave birth to the universe. The light was released when the universe was 380,000 years old.
And now we're at around 13.8 billion years. So the light propagated from this early period all the way to us, which means that the information that it carries is the information from 380,000 years.
For the microwave background, it is everywhere on all directions, and it is the intensity of them is similar. So that just tells us that, okay, it is something from earlier universe.
Every time we switch channels on an old television, we get static. Some of that comes from the CMB radiation. Dick and George tackled how structures like galaxies, stars, and planets are formed in the universe from decoding the information in the cosmic microwave background. They were fascinated by what's called dark matter.
It is what's essentially holding the galaxy together.
This is our galaxy, the Milky Way.
There is this big halo of dark matter which surrounds this and essentially gravitationally holds the whole thing together. And what was shown, in fact, Peebles played a role in this, that if you didn't have something like that, you would not be able to have a stable set of spiral arms.
Dick and George were interested in dark matter's relationship with the CMB.
And the issue was, what was the nature of that dark matter and what influence did that have on the formation of structure in the universe, and what was its impact on the microwave background?
They developed a computer code with the different elements of the early universe, including dark matter, from before 380,000 years to the present day.
The calculations we did was essentially that transport from way back when to now, and saying that if you looked at the microwave background, you would see this element that had information about what happened at 380,000 years. So it was essentially evolving the entire universe. We were the first ones to really put the whole story together that covered all of the different scales of size of the universe.
Dick and George's first major calculations on the CMB were published in a paper in 1984, but it would take years for the evidence to be discovered to support their predictions. In the following years, many ground, balloon, and space experiments were made to find out more information on the cosmic microwave background. This beach ball shows results from the WMAP satellite mission in the early 2000s.
So it's showing the way the universe looked at 380,000 years after the Big Bang. This red thing is the plane of our galaxy with lots of emissions. This is what we did with the Planck satellite. This is higher resolution and more accurate than this.
Planck was a European Space Agency's space mission from the late 90s to the early 2000s. What has stunned astronomers is the accuracy of the results. They match Dick and George's calculations closely.
Everything else has come in one after the other in terms of what we said should be there. And so that's, it's satisfying, obviously. We were dealing with the theory of the universe, which we didn't know how it was going to work out. And that it worked out to be this relatively simple theory is remarkable.
Modern computer programs used to interpret the experimental results are based almost entirely on the physics developed by Dick and George. Dick and his colleagues at the Canadian Institute for Theoretical Astrophysics, or CITA, came up with the theory of the cosmic web, which explains the structure of the universe. Fluctuations in the dark matter create clusters of galaxies. Between two clusters is a filament, and along the filament are galaxies.
The dark matter clusters. And what that means is that something that started out as little fluctuations, they become big fluctuations. And then they grow and become what we call nonlinear. And what that means is if the ups and the downs were equal, as they were at the early stages, then they become unequal as time goes on, and the regions which are slightly overdense in mass, they collapse, and the regions that are underdense have a flow of information from the underdense region into the overdense regions, and so it becomes asymmetrical. And in 3 dimensions, it leads to the cosmic web.
Bart Roberta is a professor of astronomy at CETA. He says Dick helped answer the big questions in life with math formulas.
And I think we all care to know where we come from, what is our origin, and what is our ultimate fate. And Dick gave a mathematical description that can help us understand what that fate is.
Dick's received many awards in his career, but there's one that holds a special place in his heart.
This is the Order of Canada, so it was awarded for not just being a good scientist, but also because I had impact in the development of astrophysics and cosmology across Canada. It's actually officer in the Order of Canada.
Born and raised in Toronto, Dick grew up in a middle-class family. His father was a salesman, and his mother was an office manager. His sister says Dick was a smart one in the family.
He was always curious about things, and very early age he started to read, and he read extensively.
Beginning in the 1970s, Dick liked to write down his scientific thoughts in journals.
I have this way of working where I am writing to myself all the time. That's how I actually do my creative work. But this one has a great title on it, Imagine, because it's all about imagination.
Dick and his partner Karen met professionally in 1987. He made such a good impression that she made the first move.
6 months later, I called him up, was looking, and did you remember who I was?
Yeah.
Yeah. And
your hair is completely...
and he invited me out for dinner. And we went for our first dinner on April Fool's Day.
There was a party that night that we went to, and we danced and pranced at the party.
Fast forward to today, they've raised a daughter and have an 8-year-old granddaughter. And Dick still likes to have a good time.
I tried to travel with him a lot, and it was fun because just to see all the people he knows around the world, he knows everybody, and he gets together and he loves to sit and talk, eat and have wine with them.
With the long career in cosmology, what advice does Dick have for the next generation of scientists?
Things that grew out of what George and I did was the coupling together of experiment and theory. And it started off with small teams, and it became progressively larger teams. So one of the most important things, in my view, is that people need to have the ability to, yes, be part of teams, but also not lose sight of the big questions.
Join us next week for more of the Shaw Prize Special 2025 and meet the winners of the Life Science and Medicine and Mathematical Sciences Awards, plus a laureate in Beijing.